This is Pedram from physacademy.com with a two-dimensional ultimate level practice problem. In particular, this video will discuss a relatively complicated projectile motion practice problem. This practice problem covers almost everything, I mean it, everything algebra-based student needs to know, and is also really good for calculus-based students. Alright, let's read this problem together. As usual, first we will eliminate complicated terms and then extract the variables and their corresponding values that are given. Finally, we make a list of what we need to calculate. Okay. As you see, the first sentence is whatever. And the second, alright, so the initial acceleration of object 1 is 15 meters per second squared and horizontal. You see, when we think of acceleration, we know it's a vector. Therefore, we need to pay extra attention to the direction of the acceleration along with its magnitude. Let's read the rest of the problem together. Object 1 starts at rest. It means the initial velocity is 0. Okay, and at this initial position, object 1 is 70 meters from the edge of the cliff. For object 2, velocity is constant, which means 0 acceleration. Okay, so it is a two-stage problem. First, both objects move along the straight line, so we are dealing with the 1D kinematic case. Then they hit the cliff's edge, and object 1 goes through a projectile motion. Okay, now for part A, determine the minimum constant speed that object 2 must have to reach the cliff before object 1. Okay, I'm going to think loud while working on this problem so you can hear my thinking process. First, I start with sketching a 1D coordinate system. It helps to keep track of variables and their corresponding sign, and it gives us a pretty good idea about what is happening. Here I refer to coyote as object 1 in black and a roadrunner as object 2. The coyote's initial velocity is 0 and the roadrunner's velocity is constant. Remember, in part A, we want to find a roadrunner's velocity, or object 2's velocity. Let me mark our initial location where x is equal to 0 and the final spot at x is equal to 70 meters. Remember, the acceleration of object 1 and the velocity of object 2 are constant, so we don't need an initial or final subscript for them. Let's start writing the equations of motion for these two objects along the x-axis. Remember, other than delta t, everything else here is marked with subscript x. Alright, delta t and delta x are the same for both objects. The initial velocity of object 1 is 0. The acceleration of object 2 is 0 because its velocity is constant and doesn't change. And we're trying to find the velocity of object 2. So let me mark it here again. The acceleration of object 1 is constant too. Since this is a one-dimensional case, I will leave the x subscripts off for the rest of part A. Alright, let's rewrite these two equations without any of this extra stuff. And mark our unknown, the velocity of object 2, or the roadrunner's velocity. Delta x is positive 70 meters. Just in case, here is a calculation process for it. Now let's mark the variables. We have a value for them. They were given to us. Delta x is 70 meters and the acceleration of object 1 is 15 meters per second squared. Let me mark them so you know what equation I'm referring to. You see, if I knew delta t, I could go straight to the second equation and find the velocity. Anywho, we don't have a value for it yet, but we can find it from the first equation. So, as I said, for equation 2, we can find what the velocity is, but we need to calculate delta t first. From equation 1, I can find what delta t is. I rearrange equation 1 and then plug it into the equation 2. After this, we have two options. In option 1, we plug in the values and try to simplify them from there. Remember, always write the units by the values. Let me check the units to ensure we are not leaving anything out. Meter and meter, they cancel each other out. The second squared under a square root turns to second. I have a meter on top, so we get meter per second here. Perfect. Meters per second. It is the standard unit of velocity, so we're good. Now let's continue on the numerical calculation. Alright, we get 70 divided by a square root of 28 divided by 3. Which is approximately equal to 22.913 meters per second. So the coyote cannot keep up if the roadrunner's speed is over 22.913 meters per second. Now let's see what option 2 is. We could rearrange the velocity equation a bit before plugging the values. In the end, the final equation is much simpler. Now we can go ahead and plug the value in. It leads to a square root of 525, and for the unit after checking them, we know it is meters per second, which is approximately 22.913 meters per second. Now let's work through part B. In part B, we have a classic example of projectile motion. Let me sketch a side view of the situation to better understand what is happening. So object 1 hits the cliff with some velocity straight horizontal. Then, while maintaining a horizontal acceleration of 15 meters per second squared, it goes through a free fall for 100 meters along the vertical direction. Remember, it's moving along X and Y together in the same time. We want to find how far along the horizontal axis it travels before hitting the ground. Again, we have a kinematic problem. The first thing I'm gonna do is sketch a 2D coordinate system before any calculation. Remember, based on my coordinate system, acceleration along the x-axis is constant and equal to a positive 50 meters per second squared. The acceleration along the y-axis is negative g. You could have the positive direction of the y-axis downward and assume the acceleration along the y-axis positive. Here, I will stick to the most common coordinate system students prefer to work with as shown, where the y-axis is upward. Remember, g is the Earth's gravitational acceleration, equal to 9.8 meters per second squared. In this case, since it is pointed towards the negative direction of the y-axis, we consider the acceleration of object 1 along the y-axis as negative 9.8 meters per second squared. Delta y is negative 100 meters, and we want to find the value of delta x. Delta y is negative 100 meters because we start from 100 and we end at 0. So final minus initial is negative 100. Like any 2D kinematic problem, let's have the calculation along the x and y axis side by side so we can track them together. Remember, delta t is the only variable appearing in the x and y columns. Anything else is the component of a vector and belongs to its own column. When I was learning this content, I used to call delta t the glue of coordinate systems because this is the only variable that appears in all directions of the coordinate system, and it's the same for all of them. You will see in a minute what I mean. Alright, starting with the delta x and delta y. And then continuing with accelerations along the x and y axis, and then initial and final velocities along the x and y axis. Remember, finding the impact or final velocity is what we will find in part C. And finally, delta t. Alright, again, let's start with equations of motion. Along x, I have the following equation. Here our goal is to calculate delta x. Acceleration along the x-axis is given 15 meters per second squared, but we don't have any particular values for delta t and the initial velocity along the x-axis. For delta t, we can go to the y-axis column and calculate it using y-axis parameters. Since we need to know what delta t is squared and delta t is, I will keep both of them here. Delta t squared is equal to 200 divided by 9.8 seconds squared. Delta t is equal to a square root of 200 divided by 9.8 seconds. Alright, let's work on the initial velocity along the x-axis. From part A variables, we can find this initial velocity. Since in part A, we didn't really calculate how long it takes for object 1 to get to the cliff, I'm not gonna use a time-dependent equation. Therefore, I'm going to use a time-independent equation of the motion here. First, we write the equation, then cross off the variables that are equal to 0, then plugging in the values we know, we find the velocity of object 1 at the cliff, which is equal to square root of 2100 meters per second. Now, we have all of the variables we need to calculate delta x. Let's plug them in the equation of motion along the x-axis while keeping an eye on the units. Okay, after some numerical calculation, we find that delta x is 360.081 meters. For part C, we want to calculate the impact velocity components. By components, we mean the velocity along x and y separately. And again, having the x and y axis variables side by side, so far as we know, delta x is equal to 360.081 meters, delta y is equal to negative 100 meters. Initial velocity along the x-axis or at the cliff is the square root of 2100 meters per second. The initial velocity along the y-axis at the cliff is 0. And we want to find the final velocity along the x and y axis. Before diving into more calculations, let's look at our original coordinate system again and see what sign we expect for the impact velocity components. So according to our sketch, I'm expecting a positive value for the x component and a negative value for the y component of the impact velocity because it's downward. It is a crucial step, especially when working with the time-independent equation of the motion. Because in the time-independent equation, velocities are squared, so positive or negative, they give us the same value. When we work through them backward, like this case, we need to pay extra attention and find their sign from the physics of the problem, rather than just being relied on the mathematical calculations. Alright, I'm going to write down the time-independent equation of the motion, then plug in the values and work through them to get to the final values for the x and y components of the impact velocity. So the final value of x component of the impact velocity is 113.589 meters per second. For the y component, we have a negative 44.272 meters per second. Again, we found this negative sign of the velocity by analyzing the physics of the problem. Now, let's put both of these values together as a vector. Great! Thank you for watching my step-by-step video. If you liked it, consider subscribing to my channel. This is the best way to support my work here. For more practice problems, you can check my website, physacademy.com, and have a good day.